Yeah, thank you very much for.
Go ahead. It's just the
Yeah.
announcement recording.
Okay. So thank you very much for the opportunity. I hope all of you can hear me, and I'm going to show my screen, share my screen now. Can someone confirm that you can see my screen?
Yeah, we see the whole the PowerPoint screen
Okay.
showing the slide, and then the and now you're seeing the presenter view. Yeah.
Should be good now.
Yes. Yeah.
Okay. Thank you very much. Okay. So I'm from the place that develops PSCAD. So EMT is my area of expertise. Uh, I have been involved with EMT simulations for over 30 years, and I've been heavily involved with EMT simulations for inverter-based resource integration, starting with wind for about 15 years now, pretty extensively. So I'm going to share some of my experience with you rather than anything else. I will definitely talk about EMT and areas or situations where we think EMT simulations are necessary. I know this series is about grid forming inverters, but most of my talk, the technical points are more related to grid following inverters. That's where we identify the issues and the needs. So when grid forming becomes the industry standard, right now probably less than 10% of inverters are grid forming. When grid forming becomes industry-wide, like large scale, maybe some of these challenges wouldn't be there. Maybe there'll be new challenges. Maybe the same challenges would be there. So I hope, even though the topic is not grid forming, the points that I'm going to highlight are important or will be important over the years as well. So EMT simulations, right? Why do we need EMT simulations to facilitate large-scale inverter-based IBR connections? The simple answer is the power electronics. The response of power electronics under, especially when they are being connected to weak grids, the response of power electronic devices sometimes cannot be accurately predicted based on RMS simulations only. So there have been examples, situations where uh, we have to go to more detailed type EMT simulations. So I have to establish right at this point, EMT is not replacing RMS type simulations. In my opinion, RMS simulations will be the baseline for power system planning and operations. EMT will supplement or complement or support RMS simulations. But whereas even 10 years ago, there was hardly any EMT simulations done to identify system level oscillations or instabilities. Unlike 10 years ago, there will be a bigger need to perform EMT simulations for system level analysis or studies. So during this presentation, we will try to establish why and some of the challenges as we have to do those type of simulations. To be more specific, with respect to grid following inverters, if you have a grid following inverter, the inverter controls needs to know the condition of the grid in order to do its controls correctly and accurately. Like more specifically, the inverter controls needs to measure the voltage at the connection point, the bus voltage in its magnitude and phase. It's very critical that this measurement is accurate during disturbances. If the inverter and its measuring system cannot follow the changes in the grid frequency, grid voltage magnitude, and phase, then it cannot correctly follow the grid. Because if you're following the grid, if you have to know the condition of the grid. With respect to that, There are so many details in the inverter controls that come into the picture, but more often that the phase lock loop becomes a critical component. The phase lock loop we will see, I will also show you a little later, is what tracks the so-called phase, the phase angle of the connection bus. If the phase lock loop cannot lock to the correct phase angle when the voltage goes through transients, more often than not, that could cause issues. Now, tracking of these voltage at the bus connection point correctly becomes more of a challenge when the inverter or the IBR is connected to what we call our weak grid locations, right? A weak grid location typically is uh, you identify a weak grid location typically by comparing the short, by calculating the short circuit level at the connection point and then calculating the short circuit ratio. So at locations where the short circuit ratio is low, when you have a disturbance, right, the changes in the voltage can be more pronounced than at a strong location. More specifically, the voltage magnitude and the voltage phase angle can go through larger deviations during disturbances. They can go through larger changes at weak grid locations than at strong locations. So then it challenges, puts more pressure on PLL to do a good job. This probably is a good example to highlight that. Now, what I'm trying to do here is to connect a wind plant to this location in the grid. Okay, so if I apply a fault on this line and trip this line, if you trip this line, obviously the system, the voltage here would go through a transient, right? From a steady state perspective, like this, the voltage at this bus would change its phase angle because you're changing the topology of the network. You're disconnecting a line, it's a new power flow, the voltage magnitude, but also more importantly, the phase angle could shift. And in this first simulation example, what I'm showing you is, if I did not have a synchronous condenser here, and all of us know what a synchronous condenser here is, it's a synchronous machine with no power in real power input. If you did not have the synchronous machine here, the simulation showed that the wind farm would not survive, or right through the fault and come to a stable operation. Okay. When I placed the synchronous condenser, when I added the synchronous condenser in this simulation, the response was stable after following the fault. Okay, so I want to focus specifically on this second graph here, the bus voltage angle. So the angle in this example has jumped from about 35 degrees to about 60 degrees, right? That's the magnitude of the change. That's the magnitude of the angle change. And now the synchronous condenser does not provide any real power, right? Any real power. So the synchronous condenser would not have impacted the angle jump. It wouldn't impact the angle jump, right? But why did it help stabilize the whole response? The reason for that is the synchronous condenser, because of the inertia it provides, would have impacted or reduced the rate of change of this angle. The rate of change of the angle jump would have been the same with or without the synchronous condenser, if you could have gotten this to be stable. But it is stable now because the rate of change of this angle, or the rate of change of the frequency, was slowed down due to the presence of the inertia provided by this synchronous condenser. So when things change slowly, the phase lock loop had time to track it reasonably accurately, right? So now this adding of the synchronous condenser would also increase the short circuit level, the short circuit current at this bus. What I want to highlight is what really helped this situation was not the fault current, right? Fault current was just, for me, an indication that there are synchronous condensers which provides inertia. A second point is if you had more lines connected to this bus, if you had more lines, if the transmission system was stronger with parallel lines coming into this bus, that would also increase the short circuit strength because the impedance would drop. That also helps stability of operation of IBRs, because if you had more lines, tripping one line would not have caused a big jump like this, right? So a strong transmission system impacts the voltage change, right? A presence of synchronous machines or synchronous condensers impact the rate of change of that change. So those two aspects are important when we are talking about grid following inverters. And both of these characteristics, both of these good features are characterized by the short circuit level at this bus. That's why we use the short circuit level as an indication of how strong or how weak a point of connection is. So that's a basic introduction. Next, before I talk about inverters and some simulation examples, I'm going to give you a little bit of a background on electromagnetic transient simulations, right? So at the end of the day, what we are trying to solve are circuit equations. Of course, we will also be connecting dynamic devices like inverters, synchronous machines, and they have to come into the equation as well. But the important point to note from our perspective is more so than the detailed models of dynamic devices of, say, IBRs, the solution method of the network itself. Okay, so in EMT, in electromagnetic transient simulations like in PSCAD, right, we solve the differential equations of a network. So if for this simple networks, you would write the Kirchhoff's equations relating the voltages and currents. So you can see these are differential equations, and then we solve them, right? We don't approximate anything. We solve differential equations, and we would get instantaneous waveforms, instantaneous values as our solution. So we are in EMT, the response, the solution is the instantaneous value of the voltage or the current or whatever it is, right? So that's EMT. Now I will use a second simple circuit. Once again, if you have a LR circuit of this nature, the voltage equation would be V equals IR plus L di by dt. So that would be the EMT solution. Whereas in RMS, the network part, again, not the dynamic devices. Dynamic devices are handled differently, but the network part in RMS simulation is approximated by a phasor equation. So the differential equation in EMT, it's a phasor equation in RMS. So, but you can see V equals IR plus L J L omega times I. L omega is X, and X is calculated at either 60 Hertz or 50 Hertz, right? So the network impedance is represented at 50 Hertz, whereas in EMT, you don't have a concept of frequency. It's a time domain equation, right? So that's the big difference. In doing so, when you go from a differential equation to a phasor equation, the dynamics of the network, the transients that could happen in the network are not considered. Or in other words, during a fault or a fault recovery, if your network voltages and currents go through transients like this, these transients are not considered in the RMS formulation. Unfortunately, whatever, uh, inverters, unlike synchronous machines, can perform poorly in the presence of significant or nasty network transients of this nature. Okay, so that's really what is driving the need to perform EMT studies to facilitate or get accurate responses of inverter-based devices. The impact of network transients that can impact the inverter are not accurately or fully captured if you only do RMS. Now, if your connection is near a strong grid at a strong location, the voltages wouldn't be this bad. Okay, so the RMS would also give you good accurate results. But as your connection location area becomes complex, weak with multiple inverters, that's when you have to go into these type of detailed simulations, in my opinion. So I will show you some examples based on studies that I have done for various clients. Oh, before I go there, let's elaborate a little bit more on the so-called network dynamics or network transients. This is one example, and I don't have to explain this. It's obvious what this means. This part of the waveform is not balanced and sinusoidal like in the steady state. Some other transients may include, see, in this case, this is an example from clearing a fault near a series compensated line, right? As you have in Texas area. Series compensation is also becoming more and more common across the globe world. Now, if you clear a fault, if you really analyze a simple series capacitive circuit, you can show when you clear the fault, the voltages at the connection or that location could have DC offsets, like offset in the voltage, like the blue waveform, right? Similarly, when you have faults in transmission networks, the fault current could have DC offsets, which would eventually decay and become symmetrical. Now, this is almost totally 100% a network related response. How fast this would decay depends on the losses in your network. The inverters have very little to do with the transient and the decay. However, most of you have, I'm sure, have studied this. If inverters experience an offset in the voltage, the inverter DC link voltage can go up, the IGBTs will lose control, and eventual trips might happen. So those type of issues, tripping of inverters due to this type of network dynamics, you cannot capture using RMS simulation. It's not going to happen. Uh, here are some example plots. Now, traditionally, EMT studies were performed. Okay, let me show. To identify the impact of high frequency transients on equipment insulation. That's the traditional application of PSCAD. So EMT. So in EMT studies of the past, we would be trying to model a very small area of the power system, sometimes just the substation and the surrounding one bus away type area, and focus on these type of transients. So that's the traditional application of EMT. However, now when we are talking about IBR connections, we are not necessarily focusing on the insulation of equipment. We are focusing on the stability of the grid as a whole, right? So we wouldn't probably even be looking at high frequency components in the simulation. We would be looking at the RMS voltage, power, reactive power variations, as we did in the past predominantly with RMS type programs. So even though we are using EMT for renewable integration studies, we are still looking at the quantities that we used to look with RMS type programs. Okay, so here are some results comparing the response of a EMT study versus a RMS study for a preliminary HVDC connection study we did for a client in Asia. I don't want to give too much details. So in this case, obviously they are not like it was a system-wide study. The results are not even matching exactly, but both RMS and EMT are predicting kind of a stable response, right? So, I mean, given the mathematical differences between EMT and RMS, sometimes you would accept that, yeah, like I can trust that this system under this contingency is stable. The second event, a different event on the same study, uh, RMS predicted stable response, EMT predicted, oscillatory response, right? So these, I'm just trying to show sometimes RMS may not provide the full picture. In these type of situations, we have to go dig deeper and find out what is wrong. Do we have to retune? First of all, of course, you have to make sure that the model is accurate, that this is not because of modeling deficiencies in either EMT or RMS. But once that is established, you have to go do fine tuning, and for that you generally use EMT simulations. I think I already explained this. The network dynamics like offsets in voltages and currents that could impact IBR operation and stability. Okay, so that's a little bit about EMT, the fundamental formulation of equations, and why it is required sometimes for IBR studies. Now let's talk a little bit about IBRs themselves so that we have a good understanding. Like in the grid following, we already established, right, the inverter, the voltage source inverter, VSC, which is acting as a voltage source. The role of the VSC, what we want the VSC to do is establish a sinusoidal voltage E. The magnitude and the phase of this voltage E should be established knowing the magnitude and the phase of the voltage at the grid side of the inverter, right? So in practical inverters, there will always be a inverter filter at the low voltage level, and the inverter level control measurements are always taken from this point marked as V, right? So knowing the magnitude and voltage phase angle of V, the inverter controls will establish the required magnitude and phase of E in order to meet a certain PQ demand, right? Now, so the establishment, the calculation of or the measurement of the phase is through the phase lock loop, right? And we already said that it's very critical to establish very accurately the phase angle of this voltage. It is established, it is measured using the PLL, phase lock loop, and the input to the phase lock loop in real inverters, all of you know this, the input to the phase lock loop is the actual instantaneous voltage, right? So now in EMT, you actually calculate the actual instantaneous voltage, whereas in RMS, you don't have the actual instantaneous voltage calculated, which means one of the most important components within the inverter, right, cannot be accurately represented in a RMS program, because the input to the inverter input to the PLL is the instantaneous voltage. In RMS, you don't have that. So you have to mimic this whole block. And it works. It works in most situations. But if you have to deal with voltages and currents of this nature in real life, then the approximations you make in RMS may give you misleading results. So I think this is a great example to highlight why EMT studies are sometimes required. I will skip this one. I mean, a good to elaborate on this example. During faults, when you have a fault or a low voltage right through kind of situation, it's very common for the inverter controls to take over and drop the P reference. You don't want to push P, you slowly ramp it up, or you ramp it up after the voltage has recovered. So you drop P, and in order to support the voltage recovery, you might increase your IQ or reactive current injection. So this is done at the inverter control level, right? So at the inverter control level, there would be control features to drop ID reference, increase IQ reference, and then you will go through all the calculations, decouple controls, and so on. And finally, the controls will establish a so-called D and Q axis voltage reference for fire impulse generation. Of course, D and Q axis quantities are mathematical. You have to, at this last stage of the inverter controls, you have to convert ED and EQ to the ABC reference. And this conversion is also done using the output from the phase lock loop, that theta angle from the phase lock loop. So you can see if the phase lock loop messes things up or doesn't follow or lock to the voltage accurately, all your good control strategies would be useless, right? So this is a very common occurrence under weak grid conditions, at least at initial design and study stage. This is a good example from a offshore wind farm design that we performed some years ago. So you can see there's a fault. Fault is cleared, the voltage has recovered, right? And if you look at the power right here, the blue curve, the power has also recovered, ramped up, recovered. But if you zoom in to the instant where the fault was cleared, you can see the power going in the opposite direction for a very small time interval, right? So in this case, it did not trip the inverter, nothing happened, but transmission operators don't like this power reversal. I think there's concern that this might impact existing protection, reverse power flow, whatnot. So the designers, the equipment vendors are challenged to, avoid these type of little things, even these type of little things. And this really is because once you clear the fault, your phase angle at the bus obviously would shift, and it takes a while for the PLL to lock. You can't avoid that. You can minimize these type of things, but you can't avoid that. But to do these type of, detailed analysis, you really would need to have EMT type simulations. So now, 5 years ago, this was a hot question. Do we need EMT simulations to support IBR connections? Now the industry doesn't really ask this question. There are enough examples, situations where it was shown that EMT simulations are really useful and necessary, right? The offshore wind farm design that I discussed was a good example, right? If you have these type of nasty waveforms, the operation of the inverter cannot be correctly predicted with RMS only. Another example is the right-through performance of a wind farm near series compensated lines. This example comes from the Texas area, Panhandle, Texas area. And the reason for that is the theory that I explained, potential offsets in voltages that could impact the inverter. These type of things cannot be studied only. You wouldn't catch any issues of this nature in RMS. Then this is another example where this was from Australia, relatively low voltage 66 kV system over here, relatively weak. There were number of existing wind and solar in the area, and the study was to connect a new wind farm, right? And we observed a number of issues, right? Voltage recovery, oscillations, and so on. And specific controls tunings had to be done in order to overcome the issues and to make this connection possible. So these type of issues again cannot be studied in RMS. And I want to also highlight these type of very specific issues cannot also be studied using generic models. Because if you give me a generic model, I can tune that generic model to show that there are no issues, or I can tune it to show issues. So there are certain situations where you have to really depend on or use EMT simulations, but also very specific vendor provided models. There are some other examples which I will skip through very fast because of the time constraint. In Texas, in the US, faults on the collector feeders is a mandatory study requirement, right? If a feeder that connects a number of wind turbine strips, right, would there be significant over voltages that could harm the collector design, collector system equipment, as well as sometimes the transformers belonging to the transmission system owner. So these are referred to as temporary overvoltage due to feeder tripping. Again, uh, you can't study this in anything but EMT. I will skip through these. So there are many examples where you need EMT, but the question is, do we actually need wide area EMT simulations? Or in other words, do we have to do we need EMT studies to identify issues across, let us say, the uh, do we need to model the whole state of Texas or whole country of United Kingdom or whole of Australia to identify specific issues? So these are being referred to as wide area EMT studies. uh, uh, do we need that? Like, I'm also not convinced. Like, I think you don't need to model the entire country or whatever to capture issues. If you know what you're looking at and your experience, you can identify issues by capturing a relatively large area. So there are enough examples to show that if you don't capture a relatively large area, you may miss uh, identifying certain issues. So there is a need, in my opinion, for wide area EMT simulations, but how wide that area, I think, is uh, an engineering judgment. However, having said that, if you can model an entire country and if you can perform simulations fast, just like RMS, or I mean, as fast as RMS or close, then why not? Because then you're not making guesses, you're not making approximations. So that's my take on that. Some examples are the South Australian blackout event of 2016. In order to recreate this, and now for AMO to identify critical operating situations, I mean, it was obvious that the whole South Australian network needs to be modeled. You don't want to make approximations when you have a critical concern like a total blackout. So that was one example. Now AMO is performing operational studies representing the whole of the South Australian network and sometimes the Victorian network as well in EMT simulations to identify the minimum inertia requirements in different regions to avoid blackouts due to major contingencies like tripping of a heavily loaded interconnection, AC interconnection. Okay, so that's one example. I'm not going to go through the descriptions. Second example again was first identified in Australia, low frequency oscillations, voltage oscillations. So these are 8 to 10 hertz type oscillations of very low magnitude. I can't show you this example for IP regions, but these were identified first in Australia and they were observed in England and other places as well. So in weak areas with multiple IBR plants, we have experienced very low magnitude but 8 to 10 hertz like oscillations. And we have shown that if you don't model a significantly large area, you could miss observing these issues. 8 to 10 oscillations, the magnitude is very small, but 8 to 10 is the worst frequency for visible flicker. That's why this is a major concern. And in England, we have had we have observed these type of oscillation in areas where there are multiple IPR connections, including HVDC and offshore wind. So this is another example why you may need wide area EMT studies. I have some other examples like in the UK, in the UK, we had to do a study to support the connection of 3 large STATCOMs, right, in the so-called south coast of England. Lot of other offshore wind and HVDC connections, HVDC connections get terminated in this area. There are thermal generation as well, and the power goes all the way up to London, the major load center. So when we were doing the study, like it was not possible to limit the model to a small area because the 3 STATCOMs themselves captured a wide area. So this was probably one of our first large system studies. And what I want to highlight is, of course, this when we did the study, the conclusion was we could connect the 3 STATCOMs without causing control interactions or any other oscillations. But the important point I wanted to highlight is before we did the study, we were also able to benchmark the large area EMT model with the response of the power factor based RMS model. So we knew that the EMT model was accurate before we started any studies. So that's some background. Now, what are the challenges? Obviously, in EMT, like we said, we have to solve differential equations. The solution is based on numerical techniques that we adopt, whereas in RMS, we are not solving differential equations, time domain differential equations. We are so algebraic equations. EMT simulations are thus computationally demanding and slow, right? So that is one challenge that we have to overcome. And the second challenge is when you have power electronic switches, right? Power electronic switches, when they turn on and off, that is effectively change in the system impedance matrix. Every time one of these IGBTs goes through an on-off change, the system matrix, impedance matrix change. We have to, in the calculation, we have to re-invert or recalculate the matrix, and that has a significant impact on the simulation speed, right? So we have to overcome these challenges to make large-scale wide area EMT simulations practical. So some of the research and developments that's happening to facilitate large area simulations include improved mathematical algorithms. We are investing a lot of effort on improving our algorithms at the very basic level to speed up simulations. Now, modern computers are pretty powerful. Even my laptop has, I think, 12 cores, 12 processors. So I can run some of these, some parts of my simulations in parallel simulations to speed up the overall simulation time. Now, we also have to find out better ways to represent these switching devices, right? One way that the industry has adopted is the so-called average models. So don't mistake average models for RMS models. Average models are as detailed as the switching type models, right? And they are very suitable for most of the studies that we perform at a system level. They just don't represent the switching details of the IGBT. There are no approximations in how the controls are implemented, how the PLL is implemented. So if you have to do these type of studies, or if you're asking for models from vendors, I mean, it's a good idea to get the detailed model as well as a average voltage source-based model to speed up simulations. Now, the current status, like a very large area, like let's say a part of Western Canada, USA, with over 2,500 buses, 50 dynamic devices, a very large system. Practically, we can, with the techniques we have now, can be run pretty fast, right? For example, a 30-second simulation in about less than 10 minutes, or a 10-second run in about 2.5 minutes. Typically, when we do studies, a stability analysis, we would do a simulation over around 30 seconds, typically in industry. So what I'm saying is you can have a large area study and complete one simulation in about 5, 6 to 10 minutes right now. Of course, RMS is much faster. A comparable RMS simulation would run in less than a minute, I would think. So EMT is still slow, but it's not prohibitive. So there's a lot of ongoing tasks to improve the simulation speed, accuracy, and so on, like I just explained. As we go into like more and more heavy penetrations of IBRs, I think the industry needs to be prepared, and most entities already are practicing some of these. For one, you have to make sure that transmission operators should ensure that they obtain accurate models of their plant from the vendors, right? So I think entities should have documents outlining what they need in a model, right? And then they should have a process to test the model. But really, you're not testing the model, you're testing the performance of the plant, right? In Australia, you have model quality tests, or MQTs, right? Or DMAT tests. In DMAT tests, you are not just testing the quality of the model, like model is just a mathematical model, but you are really testing the performance of the plant, like whether the plant would meet the steady state and dynamic response requirements as outlined in the grid codes and whatnot. So industry should, everyone, like not all entities, transmission operators do this in a organized manner at this point in time, but I think that's something the industry should think about. And also model benchmarking, like I said, RMS simulations would be an important aspect of system planning for years to come, in my opinion. So when you get EMT models and RMS models, you have to benchmark the models very carefully. In general, they should both give comparable results. Of course, you can't get identical results from a EMT and a RMS type model for some of the tests that you may perform, but the overall conclusions that you get from the model should be comparable. So model benchmarking should be done in an organized way as well. Finally, I want to talk about generic models. If you ask me, you shouldn't be using generic models to do very specific studies. You are doing EMT analysis because you have specific challenges. And really, as much as possible, you should try to have the vendor specific models of your IBR plants. Otherwise, I don't think you can assure the accuracy of your conclusions in challenging situations. But I mean, there are places where you can probably use generic models, especially if you, for your existing plants, if you never got the vendor models, you are left with nothing, no other option but to use generic models. I don't want to elaborate on these points, but I can share this PowerPoint with you, right? For example, if you don't have any other option, you have to use generic models. If the plant for which you are using a generic model is relatively further from the point of your study, point where you apply the fault, obviously the generic model, the generic model could be sufficient. Generic models could be tuned to, mimic all the general response, like the voltage response, reactive current response, frequency response, steady state limits. All these can be included in a generic model. But the very vendor specific features or designs like the PLL, like internal controls, like that impact the response during weak grid connections, that you cannot embed into a generic model. That's vendor's property. So that's why it's important to get the models from the vendor. I mean, when you get the models from vendor, there are intellectual property concerns. I will list it here, but I won't elaborate on it. What I want to say is, if you get the models from reputed vendors, the black box models that they provide are generally very reliable and accurate representations of their actual plant design. I guess I went a little bit over my allocated time. Hopefully this was useful. That's all I have for you today.